Let's take a look at some of the bitwise operators that are available to us in the C programming language. These are going to work on the bit levels of the values of our variables. So since we are working at the bit level, we cannot deal with floating points because floats are stored in a totally different format, in IEEE floating point format. They're not considered bitwise when they're in the variable, so no floats. Integrals only, integers, characters, ints, shorts, longs, no floats or doubles from this point out. We have AND, OR, XOR, left shift, right shift, and one's complement. Do not worry if you don't get these. If you don't understand these, or you don't have to understand them right now, you may not ever even use them in your C programming career. These are mostly used by people that are programming in C in an embedded format, is what they call it. They're writing programs that are going to be inside appliances or cars or most likely some piece of machinery that they need to be able to check on the values of registers to see if a motor is turning or running, or if there's a certain temperature being set. And they will set and look at these bits and change the bits and move binary values around inside these variables. So that's why these things are in the language, but they're at this point in K&R, and I just want to show them to you, give you an idea of what they are, how they're used. We won't even go into why they're used, like exclusive ORs and things like that. You can get into some pretty intense logic discussions there, and that's not what we're here for. So let's take a quick look through the bitwise operators. Here's a single ampersand, which is an AND. Remember that we had a logical operator of AND that was two ampersands together. This is just one. This is a bitwise AND. And what this will do is mask bits. It will take bits out of consideration. So there, let's say we have X has a value of 193. This is 193 in binary. So this means that these bits are set 128 and 64, and a 1 down here gives us a value 193 in binary. We're going to have a new variable called y is going to be set to x ANDed with a hexadecimal value f0, fox0. This is the value f0, a 1 in all of these high order nibble positions and a 0 in the low order nibble down here. So this is f0. And we don't care what the decimal value is, the numeric value. We care what the hexadecimal value is with all these bits turned on, because that's our mask. So if we mask this together, if we AND this together, the only bits that will come through are the ones that are in this byte, because in this part of the byte, we say if this bit and this bit are both set in the mask, then the bit down here should be set in the result. These bits are not set in the original value, but they are in the mask, but it still doesn't work out to be an AND, so we get zeros down here. And down here, we're not masking these. We don't want to see those down there, so this one does not come through. So we only get whatever bits were set in the high order nibble of our byte of 193. So here we have ANDed with F0. And our result will be 192, which is 128 and 64. That's these two high order bits right here. So that's a bitwise AND. This is called an inclusive OR. And this is used to turn bits on in a value. Again, we start with our 193, 11000001, and we say that y is equal to x ORed with our F0. There's our F0 again, and our result is 241, because what we say is if this bit or this bit is turned on, then the result should be turned on. If this bit or this bit, then it should be on. This one or this one, it'll be on. This one or this one turns on. This bit or this bit are not turned on, so we get a 0. This one or this one, nope. Nope. This one or this one? Yes, that one's on, so that brings that bit down, and our new value is 241. So that allows us, when we OR things, to make sure that bits are turned on. And if bits are already on, that's okay, they'll still pass through. But the OR will make sure that we get these two turned on as it comes through. This is the exclusive OR operator from our Bitwise operators set, and it's the caret, little up arrow there. And exclusive OR means one or the other, but not both. So here if we have our 193, that's the binary value for that. Y is equal to X, exclusive ORed, or XORed they call it, with F0, that's our pattern. All ones there, zeros there. Y will be equal to 62, because we will look at these bits character by character, bit by bit, and an exclusive OR checks this bit and this bit. Is this bit set or this bit set, but not both? Well, here we have both set, so that means it does not make it through as false. Here they're both set, and that does not come through. Here, that one's not set, but that one is. So that does match one or the other, but not both. So we will get a true value out of that. Same thing here. This comes through. Now here is one or the other set. No, they're not. So that's false, false, false. And this one, yes, that one is set. That one is not. That matches our exclusive OR and does make it through. So our new value after being exclusive ORed with F0 is 62. That's the exclusive OR operator. Here's our Bitwise operator's left shift, and what this does is cause our value to be shifted to the left as far as the bits go. In the binary format, shifted a number of bits to the left. So here we have our X is 193. There's our value, and our new value will be equal to X left shifted by 2 bits. So we're going to take the whole thing and run it to the left 2 bits. So this 1 winds up here because it's shifted over by 2, and the 2 ones that were right here roll off into space. They disappear. These bits are padded in with zeros at the end. New bits coming in either way will be zeros. So our new value is 4. And they use this sometimes to move bits around from a register from one place to another, but you probably won't have a great use for it right away. But that's a bitwise left shift. We also have a bitwise right shift. And the right shift, again, we start with our 193 right here, and now Y is equal to X right shifted by 2. And this causes these 2 ones to shift down to here because they're right shifting by 2, and then our 1 that's here falls off into space and goes away. So we're left with zeros there. The new bits that came in are also 0, so we get a new value of 48, and that's a bitwise right shift. The tilde, or this little squiggly here, it's a tilde, is called the ones complement. And ones complement will flip all the bits. Whatever the value they are when you start out, they'll be reversed when you're finished up. And this is called a unary operator because it only has one operand. Before we had 2 things. We had one value operated on by another value. Ones complement's a unary operand, so we only have the one operator character here working on a single operand. Y is equal to the ones complement of X. X is 193. There's our bit pattern. And here is Y equal to 62 at the end, because the ones complement of X is all bits flipped. 0011 instead of 1100, and here 0001 turns into 1110. And so that is our result. The ones complement of 193 is 62, flipping all the bits. Well, that's all of our bitwise operators that we need to really concern ourselves with. So let's move on to some other types, operators, and expressions.